morning, everyone. I am Jingyao Luo from Shanghai Typhoon Institute. Today, I'm going to talk about a direct assimilation of radar reflectivity using a convective-scale EnKF system. As we know, the tropical cyclone intensity forecast is still a challenging problem in research and operational forecast. Radar is one of few observation platforms capable of observing TC internal structures and the circulation of precipitation at high spatial and temporal resolution. EnKF is able to deal with complex ice and multi-moment microphysics and more suitable to assimilate data radar directly. So in this work, we use EnKF to assimilate radar reflectivity directly. So the reflectivity operator we used is developed by CAPS. This is the reflectivity operator equation, so which transfers the hydrometer variables and also the concentration number to radar reflectivity. And this operator is based on the multi-moment, double moment microphysics. So the concentration number, the NT, is not the prognostic, variable rather than the fixed the number. So how about the experimental design? We use WOLF and GSI EnKF with 14 members, 3 kilometer resolution. So the observation we used is the composite observation radar reflectivity, and this is our domain and the distribution of the observations. So we applied our system to a tropical storm case, and we start here with GFS analysis and add some perturbations, and then run 40-member ensemble forecast for 5 hours, and from here we start cycle the EnKF radar reflectivity assimilation every 15 minutes and followed by 18-hour forecast. So we choose all of them as our analysis control variables, including not the hydrometer variables, but also some large-scale variables such as the UVW temperature, pressure, these large-scale variables. So this is the result about the first cycle. So we could say the background is much stronger than the observation, and after radar DA, we could see the analysis is much closer to the observation. So this is the result of the third cycle. Again, we could see the background is also stronger, and after assimilation, the analysis is closer to observation. But we emphasized here is the low DA is even worse than the background. But that is not surprising because the model tended to over-predicted the precipitation, and the low DA accumulated the bias. So this is the final cycle. So we could say the observation and the analysis. So we could say the analysis is quite similar to the observations. Why radar DA is better? Along this line, we plotted the vertical section of the analysis increment. So we could see the QR, QS, QI all decreased. So which after the assimilation, so we could I'm sorry. So which result in the precipitation, as we shown in the previous slides. So we also check other variables such as the horizontal wind, the vertical wind, and the temperature. All of them are also decreased. So we think after the radar reflectivity assimilation, the cross covariance could also use the cross covariance. These variables are also decreased. So we think we got the dynamic consistent analysis state of variables. So since we continually assimilate the radar reflectivity, at the final cycle, the hydrometer is in radar DA experiment is much weaker than the low DA experiment. Finally, we compare forecast result initialized from these two experiments. So the black line is the best track, and the blue line is low DA, and the red line is the radar DA. So we could see little impact on the track forecast, but for intensity forecast, we could see the significant positive impact on the intensity forecast. So we could see the red line is much closer to the best track. As for precipitations, so this is the 1 hour forecast. We could see the radar DA experiment is also closer to the observation and is better than the low DA experiment, especially in this area and in this area. So if we last for 2 hour forecast, we could see the difference between these two experiments is getting smaller, but still could see the but still visible the improvement of radar DA could see in some area, such as this area. So all the previous slides we showed is based on the double moment schemes, the Thomson scheme. But we did some additional experiment with the single moment. The result is quite different. But we could. But whatever what scheme we used, with or without DA, the result is different. After DA, it will get a positive impact on the intensity forecast, such as the red line is the mean scheme with DA, and the green line is the mean scheme without reflectivity DA. So we could say after assimilate the radar reflectivity, even in the single moment scheme, the result is closer to the observations. So that's in the summary. So a convective-scale EnKF system was successfully applied to directly simulate radar Z data for typhoon case, and radar Z assimilation has a positive impact on intensity and participation forecast. The forecast on participation maintained at least 1 hour, while the impact on intensity can last for 12 hours. And the EnKF will update not only hydrometers, but also other cross variables like UV, temperature, W, such as to produce well-balanced analysis state. So, thank you.